Hi there. In this video, we're just going to take a quick look at what is a vector function, how do we find the derivative of a vector function, and what is the unit tangent vector. So the easiest example to understand a vector function would be to perhaps consider the position vector r. And of course, we know that it has three components, one in the x direction, in the y direction, and also in the z direction. So these three components, we could think of them as being functions of time. So we would just say that these components are parameterized. So they are functions of time. So what this means is that this position in space basically just changes depending on how much time has elapsed or how far some kind of particle has moved along a curve after some time. So we could just take a random curve and we could have a particle at a certain point P away from some origin, and where it currently is on the curve is its position vector r. Then we can think of some time later, right? Some time later, it's moved a certain distance to some new position q, okay? And that's a result of some time changing, okay? So this is t plus delta t. So what do we understand by the derivative? What is the derivative of this position vector? Well, the derivative we could understand is the change in position. So this change in position, we could call this delta r. And if we take delta r and divide it by delta t, we're understanding the rate of change of this position with respect to time. And then as time approaches 0, or as delta t approaches 0, then what this means is that this rate of change of position with respect to time becomes dr dt. And to compute this, it's a fairly simple matter. Dr dt is just equal to the components, each component with respect to time, the derivative of each component with respect to time. Dr y dt, and of course our y component, and lastly the z component with respect to time in the z direction. So this is a fairly straightforward thing to compute. If we want to understand this, what it means geometrically, we can think of this time slowly approaching 0, and there's one important fact that comes out of this, and that is at our certain point P, we have our position vector, that's r, and we still have our curve, right? However, we can see that this change in position, right, is this vector pq. So as t becomes smaller, what this means is that it starts to become the tangent to this curve. So that's an important point. So dr dt is simply the tangent of this locus at P. So let's just write that down. So the direction of dr dt is the tangent to P. So if we wanted to just implement this in a simple example, we could just think of some position vector r having x component 3t squared plus 4 I hat plus 2t minus 5 j plus 4t cubed k. So dr dt would simply just be the derivative of the first x component with respect to t. That gives us 6t I hat, and then continuing in that same manner, we get 2j, and then lastly plus 12t squared k. So if we wanted to find the second derivative, we would just find the derivative of the first derivative. And that's just 6i plus 24t. And of course, j being a constant, that just gives us 0. So if we wanted to find the magnitude of these vectors, all we would just do is apply theorem of Pythagoras. But first, let's just choose a value of t. Let's just say t is equal to 1, so 1 second. So when t is equal to 1, then the derivative of r with respect to t is just equal to 6 times 1, which is 6, plus 2j, plus 1 squared is just 1, 1 times 12 is 12, plus 12k. So the magnitude of this dr dt would simply be the square root of 6 squared, which is 36, plus 4, 2 squared, plus 12 squared, 144. So 36 plus 4 is 40, 40 plus 144 is 184. So moving along, we now need to find what is the unit tangent vector. So the unit tangent vector, as we would have described it earlier using our diagram, if we look at our point P again, as we have depicted it, along some curve, and we have a position vector relative to some point of origin. And we saw that the tangent vector, so dr dt, lies tangent to the curve at that point. So if we want the unit tangent vector, so the unit tangent vector is merely just dr dt, but a unit vector in that same direction. So you'd remember that the magnitude of a unit vector is just 1. So how do we get the value 1? Well, we just divide it by itself. So what we have to do is simply take dr dt and divide it by its magnitude. So there is some unit vector. So let's just draw it in a different color. So the unit vector in this direction, call it t. So t is just equal to this dr dt divided by the magnitude of dr dt. So this is just a fairly simple matter to implement. We could take numerous examples to illustrate this point. So let's just do an elementary one. If we have some kind of parameterized curve where x is equal to 2t and y is equal to t squared plus 3 and z is equal to 2t squared plus 5. And the question is, what is the unit vector? We want the unit tangent vector, unit tangent vector at the point 2, 4, 7. Okay, so what do? Well, we write our position vector in terms of its components. So we'd have 2t as the x component and t squared plus 3 as the y component and 2t squared plus 5 as the z component. So if we find our tangent vector, that's dr dt, then all we do is we just get 2 plus then derivative 2t j, and then derivative 2 times 2 is 4, we get 4t times k. Sorry, this is a cubed here. Let's make this a cubed. So 3 times 2 is 6, and then we get 6t squared. So let's just again choose a value. So let's just say, well, we don't choose a value here. We want after how long, how much time has elapsed since it is at this point. Well, it's now at this point 2, 4, 6. And to calculate that time, well, we can just see that x is equal to 2t and x is equal to 2, right? So we just substitute in 2, and then we can see that this particle is at this point after a unit of 1, be 1 second or 1 minute or whatever it is the case. So we can just substitute this value of 1. We get dr dt when t is equal to 1. So we get 2, and then 2 times 1 is again 2, the y component, and then plus 6. So in order for us to find the unit tangent vector, all we need to do is we take our tangent vector in the numerator and we divide it by its magnitude. So the magnitude of dr dt is just equal to the square root of 2 squared, which is 4. Again, 2 squared, 4 plus 6 squared, which is 36. So 36 plus 4 is 40, plus 4 is 44. So we have the square root of 44. So if we were to now find our unit tangent vector, t is equal to the dr dt divided by the magnitude of dr dt, then this is just equal to our vector multiplied by the unit tangent vector, 1 over the unit tangent vector. So we would simply have 1 over root 44 into 2i plus 2j plus 6k. We could simplify it further. We could take out 2 as a common factor and try that sort of thing. But this is just to illustrate the point. So lastly, just a few things to note when it comes to finding the derivatives of vectors. So if we want to find the derivative of the sum of 2 vectors, this is a fairly simple matter. It's just the derivative of the one vector, and we can simply add it to the derivative of the other vector. So if we wanted to find the derivative of the dot product of 2 vectors, this is simply equal to the dot product of the first vector multiplied by the derivative of the second vector plus the second vector with the dot product of the first vector. And then if we wanted to find the derivative of the cross product of 2 vectors, then what we can do is take the first vector and then compute the cross product with the derivative of the second vector, and we add this to the derivative of the second vector, sorry, the derivative of the first vector with the cross product of the second vector. So these things are fairly simple to prove, and they can be easily illustrated. But that's not really the point of this. It's just to show how the different vectors should be taken. We should take the derivative. So lastly, if we have components, so we have a vector f, and it's made up of components that are functions of more than one variables. So x could be a function of u and v, y is also a function of u and v, and z is a function of u and v. So we can just take partial derivatives. So we'd say the partial derivative of f with respect to u would just be dx du I plus dy du j plus dz du k. And it's the same with v. We would just take the derivative with respect to v, and it would be dx dv, and then dy dv, and then lastly dz dv. So the second derivatives and mixed partials can be done in the same way. So just to summarize this video once more, we can think of a vector function as being 3 components. We looked at position as an example. We looked at what the derivative of a vector actually means, and we saw that it's something fairly easy to compute. We simply just find the derivative of each component, and we see that the derivative of it is actually the tangent at this point. And then after that, we can compute the unit vector. So the unit vector is just simply the tangent vector, but we would need to just divide by the magnitude to get that value. And lastly, we looked at different ways in which we can compute the derivative of various combinations of the products of derivatives. So in the next video, we're just going to look at what is a vector field, what is a scalar field, and the gradient of a scalar function, and also what is the directional derivative.